2:09 p.m., Monday, May 4th, 2026. Eastern Samar, Philippines. The ground moves. A magnitude 6 earthquake. Shallow, or maybe not, and that disagreement matters enormously, but we'll get to that. What matters right now is the timing. Less than 48 hours earlier, Mayon Volcano had just finished one of its most violent eruptions in recent memory. A paroxysmal eruption, not a rumble, not a steam vent, a full column paroxysm. And the shaking in Eastern Samar starts before the ash has even settled. 48 hours. That's the window sitting at the center of everything that follows in this video. Is it a coincidence? Two unrelated events that happen to stack on top of each other in a geologically restless country? Or is there something running beneath both of them? A pressure, a system, a chain of cause and effect that connects a volcano on Luzon to a seafloor rupture 400 kilometers away. Here's what we know happened, in sequence. Mayon erupted, paroxysmal phase, sometime in the 36 to 48 hours before the quake. PHIVOLCS, the Philippine Institute of Volcanology and Seismology, was already tracking elevated activity. Then the quake hits Eastern Samar, and at the same moment, PHIVOLCS is maintaining active alert status not on one volcano, not on two, on 4 Philippine volcanoes simultaneously. Mayon, Canlaon, Marapi. 4 active alerts, 1 earthquake, 1 48-hour window. The Philippines sits on one of the most seismically violent pieces of real estate on Earth. That's not rhetoric, it's architecture. The country is the surface expression of a collision that has been running for tens of millions of years, and the crust there does not rest. Earthquakes and eruptions are not rare. But the clustering of events in this window, the timing, the simultaneous alert levels, the specific language PHIVOLCS used in its bulletin caught the attention of people who watch this system professionally. Because some things are background noise, and some things are a signal. What we don't know yet is which this is. The science of whether eruptions and earthquakes can trigger each other is genuinely unsettled, not in a hand-wavy, more research-needed way, but in the data points in opposite directions depending on which studies you read way. We'll get into that. But first, you need to understand the full weight of what PHIVOLCS actually put in writing, because the language they used is not normal. And if you read it without knowing what it usually sounds like, you'd miss exactly how unusual it is. PHIVOLCS issues bulletins constantly. That's the nature of the job. A country sitting on this kind of geology generates seismic and volcanic data around the clock, and the agency puts out routine advisories the way a weather service puts out forecasts. Most of them say what you'd expect: elevated tremor, minor ashfall, residents within the permanent danger zone advised to remain evacuated. Standard language for a non-standard place. What appeared in the bulletin for the May 4th Eastern Samar earthquake was not that. Damage is expected. 3 words. If you've read enough official agency communications, you know that phrase doesn't appear by accident. Scientists and government communicators spend enormous effort on bulletin language precisely because the words carry legal weight, drive evacuation decisions, and shape public response. Agencies default to cautious, hedged phrasing. Damage is possible. Some structures may be affected. The act of construction, damage is expected, is a statement of near certainty. It means the models, the ground motion data, and the agency's assessment of local construction quality all converged on the same answer. This is going to hurt something. That language alone would make the bulletin unusual, but it wasn't issued in isolation. At the same moment, PHIVOLCS was processing the Eastern Samar quake. The agency was simultaneously maintaining active alert status on 4 Philippine volcanoes. 4, not one restless mountain in the background while everything else sits quiet. 4 separate systems, each with their own monitoring teams, their own evacuation radii, their own communities inside the danger zones. Mayon at alert level 4, the highest sustained level before a full eruption declaration. Canlaon active, Marapi active. The system wasn't reacting to one event, it was tracking a cluster. That's the thing that stands out when you look at the full bulletin picture rather than any single line. It isn't one unusual phrase or one elevated alert, it's the simultaneity. 4 active alerts and an earthquake bulletin using damage-certain language, all issued within the same operational window by the same agency. People who monitor these systems for a living describe a background hum, the ordinary level of Philippine tectonic noise that you normalize after long enough. What they flagged here wasn't the volume of any single signal. It was that multiple instruments were all reading loud at the same time. Whether that means anything physically connected, whether these events are causally linked or just coincidentally clustered, is exactly the question the science struggles to answer. But the language PHIVOLCS chose tells you they weren't treating this as routine noise either. So here is where the science gets genuinely strange. Two of the world's most capable seismic monitoring agencies looked at the same earthquake at the same moment and came back with answers that are 63 kilometers apart. PHIVOLCS reported 73. That isn't a rounding difference. That isn't a calibration tweak. 63 kilometers is the distance from the surface down through the crust and into a completely different layer of the Earth, and which one is correct changes everything about what this earthquake actually was. Here is why that matters physically. The Earth beneath the Philippines is not a uniform block. It has structure. The outermost layer, the crust, runs roughly 10 to 30 kilometers thick under the seafloor in this region. Below that sits the upper mantle, denser, hotter, behaving under pressure in ways that crustal rock simply does not. A 10-kilometer event ruptures inside the crust. A 73-kilometer event ruptures in the mantle wedge, in the zone where the subducting Philippine sea plate is actively diving beneath the Eurasian plate. Those are not the same physics. They are not even the same type of earthquake. A shallow crustal rupture at 10 kilometers tends to deliver its energy almost directly upward. The shaking at the surface is sharper, more violent per unit of magnitude, and the aftershock sequence tends to be denser and longer. If PHIVOLCS is right, what struck Eastern Samar was a crustal fault releasing stress close to the surface, the kind of event that produces the worst ground damage relative to its size. A 73-kilometer rupture is a different animal. At that depth, you are in subduction zone territory, what seismologists call an intraslab event. Stress fracturing within the descending plate itself as it bends and heats and tears under its own weight. The energy has to travel further to reach the surface. It tends to spread over a wider area but with less concentrated violence at any single point. The tsunami risk profile also shifts at that depth. And then there is the volcano question. The mechanism by which a deep subduction zone quake might interact with a volcanic system above it is entirely different from how a shallow crustal rupture would. Stress transfer, fluid migration, the unclamping of magma pathways, the geometry changes completely depending on where in the Earth the rupture actually initiated. If you want to know whether this earthquake and Mayon's eruption are physically connected in any meaningful way, the depth is not a detail. The depth is the question. The disagreement itself is not unusual. Agencies work from different seismic networks, different processing algorithms, different arrival time data from different stations. In the first hours after a significant event, depth is always the hardest parameter to pin down. It requires good station coverage at multiple azimuths, and seafloor events are notoriously difficult. Preliminary solutions shift. Both agencies will revise. But sitting in that gap, that 63 kilometers of unresolved Earth, is the entire physics of what happened beneath the seafloor on May 4th. And until it closes, any confident claim about what this earthquake means, what it might do next, or whether it has any relationship to the volcanoes burning across the arc, is built on a foundation that hasn't been confirmed yet. While that depth question was still open, Mayon had already done what it came to do. A paroxysmal eruption is not simply a large eruption. The word carries a specific weight in volcanology. It describes a sudden, violent intensification. A volcano that has been building pressure and then releases it in a concentrated burst that can compress days or weeks of eruptive energy into hours. Lava fountains, pyroclastic density currents, ballistic ejecta traveling faster than a commercial jet. The kind of event that doesn't give communities time to recalibrate. Paroxysmal is the word scientists use when they want to say, this was the worst version of this. Mayon is one of the most reliably violent volcanoes on Earth. It sits on the eastern coast of Luzon, a nearly perfect cone rising to 2,400 meters above sea level, and it has erupted more than 50 times in recorded history. What makes it particularly dangerous isn't just the frequency, it's the geometry. That steep symmetric profile means pyroclastic flows have almost no friction to slow them. Material that leaves the summit travels fast and far, and the slopes are populated. Hundreds of thousands of people live within the shadow of its alert zones. In the 48 hours before the Eastern Samar earthquake, Mayon produced a paroxysmal eruption. Lava fountains breached the crater rim. Pyroclastic density currents, superheated avalanches of gas and fragmented rock moving at highway speeds, swept down multiple flanks simultaneously. The ash column punched into the upper atmosphere, and ashfall blanketed communities across several provinces. PHIVOLCS had already elevated the alert level and enforced evacuation zones before the eruption peaked. They were watching it build. That violence matters for more than the immediate human cost. A paroxysmal eruption involves the rapid depressurization of a magmatic system. Enormous volumes of gas and molten rock moving through conduits under the edifice. changing the stress state of the surrounding crust in ways that are measurable and, in some cases, consequential for the faults nearby. Whether that stress change was large enough and whether it reached far enough to have any relationship to what ruptured 2 days later beneath the seafloor off Eastern Samar, that is the contested question aside for a moment, and just hold what Mayon did. In less than 48 hours, before the earthquake arrived, it had already forced evacuations, already buried crops and rooftops under ash, already sent pyroclastic material racing down flanks that generations of farmers have lived on because the soil is extraordinarily fertile, because Mayon has been doing this, here, for as long as anyone has kept records. The earthquake didn't start this crisis. Mayon had already opened it, and Mayon is not alone in this. While Mayon was producing its paroxysmal eruption, and while the seafloor off Eastern Samar was preparing to rupture, 2 other volcanoes were already burning. Mount Canlaon on the island of Negros in the central Philippines has been in eruption. Mount Merapi, not to be confused with Merapi in Java, sits in West Sumatra, Indonesia, roughly 2,000 kilometers to the southwest. Both are elevated on alert. Both have been producing ash columns and pyroclastic material. Both sit on the same fundamental architecture that produced Mayon. To understand why that matters, you need to see the shape of the Western Pacific from above. The Philippine Arc is not a single volcano or a single fault. It is a chain, a curved line of volcanic islands and submarine peaks that traces the boundary where the Philippine sea plate grinds westward into the Eurasian plate. That collision has been running for tens of millions of years. The subducting slab descends, heats, releases water into the overlying mantle, and that water lowers the melting point of the rock above it. Magma rises. Volcanoes form. The arc is, in the most literal sense, a product of a plate disappearing into the earth. Canlaon sits on that arc. Mayon sits on that arc. The fault system beneath Eastern Samar is generated by that arc. They are not neighbors by accident. They are expressions of the same underlying stress regime, the same subducting slab, the same system of fractures and conduits that has been building pressure across this entire region. Extend the line further, and you reach Merapi. Sumatra rides a parallel subduction system, the Sunda Arc, where the Indo-Australian plate descends beneath Eurasia along the same general logic. Different plates, but the same planetary mechanism. The Western Pacific is a region where subduction dominates the tectonic landscape, and subduction systems do not stay quiet in one place while staying active in another. They communicate, not through some mystical connection, but through the physical reality that the slab is continuous. The stress field is shared, and a perturbation at one point propagates. 3 volcanoes erupting within days of each other across this arc is not, on its own, proof of anything. These systems erupt on their own cycles, but it is not random noise either. The arc is alive, restless in a way that is measurable across hundreds of kilometers. And the earthquake off Eastern Samar did not happen in a vacuum. It happened inside a system that was already moving. So what is that system, exactly? Because the arc is alive is a phrase, not an explanation. The architecture underneath the Philippines is one of the most complicated tectonic environments on the planet, and understanding it is the only way to understand why an earthquake off Eastern Samar and 3 erupting volcanoes are not 3 separate stories. Start with the collision. The Philippine sea plate is moving westward, grinding into the eastern edge of the Eurasian plate at roughly 6 to 8 centimeters per year. That is not slow in geological terms. That is fast. The boundary where they meet runs roughly along the Philippine Trench, one of the deepest oceanic trenches on Earth, plunging to more than 10 kilometers below the surface off the eastern coast of the country. Eastern Samar sits almost directly above this boundary. When the ground shook on May 4th, the epicenter was essentially on top of the collision zone. But the Philippines is not just sitting between 2 plates, it is being pulled apart from multiple directions at once. To the west, the South China Sea basin is colliding with the main Philippine island chain along the Manila Trench. The result is a landmass caught in a genuine tectonic vice, subduction happening on the east, collision happening on the west, and the entire archipelago threaded through with a network of faults that accommodate the accumulated strain. The most significant of these is the Philippine Fault Zone, a left lateral strike-slip fault that runs nearly the entire length of the archipelago, over 1,000 kilometers, from northern Luzon down through the Visayas. It is not a subduction fault. It is a shear zone, where the 2 sides of the Philippine landmass are sliding past each other in opposite directions. This fault has produced some of the deadliest earthquakes in Philippine history, and it passes through the same island chain where Mayon and Canlaon sit.
Then there are the volcanic arcs themselves. Mayon, Canlaon, Bulusan. They are not sitting on top of the main collision boundary. They are sitting above where the subducting Philippine sea plate has descended deep enough and hot enough to release water into the mantle wedge above it, lowering the melting point of the rock, generating magma that rises. The volcanoes are the surface expression of subduction happening roughly 100 kilometers beneath them. This is what makes the architecture so important. The earthquake off Eastern Samar, whether it ruptured at 10 kilometers or 73, occurred within a system where the stress sources are stacked vertically. Shallow crustal faults, the deep subducting slab, the mantle wedge generating magma above it. These are not independent layers. They share a stress field. A perturbation in one is a perturbation in all. The question is whether that perturbation was large enough to matter is exactly where the science stops being clean. The idea that volcanoes and earthquakes can trigger each other is not fringe. It appears in peer-reviewed literature going back decades, and it has real physical mechanisms behind it. But the research is genuinely, stubbornly contested in ways that don't get resolved by reading more papers. The uncertainty isn't a gap waiting to be filled. In a lot of cases, it's the finding.
Start with the direction most people assume. Earthquakes triggering eruptions. The mechanism is plausible. A large earthquake reshapes the stress field around it. It can compress or decompress magma chambers. It can open pathways that were previously sealed. It can shake a volcanic system that was already primed and push it past a threshold. There are documented cases. The 1980 eruption of Mount St. Helens was directly triggered by a magnitude 5.1 earthquake that destabilized the volcano's north flank. After the 2011 Tohoku earthquake in Japan, volcanic tremor increased at several volcanoes across the arc within hours. But here's where it gets complicated. The Tohoku case looked clear in real time. Retrospective analysis made it murkier. Some of the apparent volcanic responses turned out to be seismic noise. Some were real tremor but showed no progression toward eruption. The earthquake happened. The signal happened. Whether one caused the other, or whether both were responses to the same deeper stress reorganization. That's harder to isolate than it sounds. Now reverse the direction. Can eruptions trigger earthquakes? This one is even less settled. The physical case exists. A paroxysmal eruption releases enormous pressure from a magma system. That pressure removal changes the stress on surrounding faults. Magma intrusion along a dike can also push stress into adjacent crustal rock. There are examples in Iceland and Hawaii, where intrusion events preceded earthquakes on nearby faults by hours to days.
But the Mayon eruption finished roughly 48 hours before the Eastern Samar quake. The quake occurred over 200 kilometers away. At that distance, the static stress change from the eruption, the permanent reshaping of the stress field, would be, by most models, vanishingly small. Not zero, necessarily, but small enough that most seismologists would not consider it causal without additional evidence. Dynamic triggering is a different argument. When a large earthquake or eruption sends seismic waves through the crust, those waves temporarily perturb stress across much larger distances than the static field does. There are cases of dynamic triggering at thousands of kilometers, but dynamic triggering from an eruption, rather than from a large earthquake, is far less documented. The waves are different. The mechanism is less established. What the research actually shows, underneath all of this, is a pattern that resists simple narrative. Volcanic arcs in subduction zones see correlated activity. Eruptions and earthquakes clustering in time, more often than chance would predict. The Philippines has shown this repeatedly across its recorded history. But correlation across a tectonically active arc, where stress is constantly being loaded and released from multiple sources simultaneously, does not tell you which event caused which. It might tell you that everything is responding to the same underlying driver. That is an uncomfortable place to sit, but it's where the honest answer lives. Two events, 48 hours apart, 200 kilometers apart, in one of the most seismically and volcanically active systems on Earth. The architecture connects them. The physics allows a link. The data, right now, cannot confirm one. That 63-kilometer gap isn't a rounding error. It isn't two agencies splitting hairs over instrumentation. It is a fundamental disagreement about what kind of earthquake this was. And that distinction changes nearly everything downstream. How it damaged structures, how it will behave in the aftershock sequence, and whether any link to the volcanic activity above is even physically plausible. Start with the shallow number, 10 kilometers. That puts the rupture in the upper continental crust, the brittle cold rock that sits beneath Eastern Samar's surface. Shallow crustal earthquakes are, kilometer for kilometer, the most destructive kind. The energy has almost no distance to travel before it reaches the surface. Ground motion is violent, abrupt, and localized. Buildings don't sway, they jolt. The shaking duration is short, but the peak acceleration can be enormous. Liquefaction, landslides, surface rupture.
All of these are more likely when the source is 10 kilometers down than when it's 70. Aftershock behavior is also different. Shallow crustal ruptures tend to generate vigorous aftershock sequences that track the original fault plane. In a region like Eastern Samar, where fault geometry is complex and poorly mapped, that means the next week carries real risk. The main shock stresses a zone of crust. The aftershocks redistribute that stress along adjacent segments. You can have magnitude 5 aftershocks that cause independent structural failures in buildings already weakened by the main shock. Now take the deep number, 73 kilometers. That puts the source inside or very near the subducting Philippine sea plate, the slab that is actively diving beneath the Philippine archipelago. This is a fundamentally different animal. Intermediate depth slab earthquakes release their energy from a source that is 6 times farther from the surface. The shaking is broader, slower, more rolling, felt across a much wider area, but with lower peak acceleration in any one place. Ground deformation is less severe. Landslide risk drops. But here's where the volcano question gets interesting again. A 10-kilometer crustal quake sits close enough to the volcanic system above it that stress transfer is at least conceivable. The same crust hosting the magma plumbing could be the crust that ruptured. A 73-kilometer slab event is mechanically decoupled from the shallow volcanic edifice. The stress field it perturbs is deeper, different, and reaches the surface through a much longer path. The link becomes harder to argue not because it's impossible, but because the geometry makes it more remote. Which reading is correct matters enormously for the people living there right now. One answer tells emergency managers to watch for aftershocks on shallow local faults. The other tells seismologists to track a subducting slab. Both agencies are working from the same seismic waves. The disagreement is real, and until a more detailed analysis of the waveforms and fault mechanism is published, the honest answer is that we don't yet know which version of this earthquake we're dealing with. That uncertainty, which earthquake, which fault, which depth, doesn't pause while the analysis gets done. People are living inside the danger radii right now, and the agencies responsible for their safety have to act on incomplete information. That's not a failure of science, that's the job. PHIVOLCS is currently holding active alert status on 4 Philippine volcanoes simultaneously. 4. That is not a normal operating condition. In a country that sits on one of the most volcanically active arcs on the planet, the agency is accustomed to monitoring dozens of restless mountains, but running concurrent elevated alerts across multiple systems at once stretches resources, splits attention, and forces prioritization decisions nobody wants to make. The alert level system itself is worth understanding, because the numbers are not decorative. Alert level 0 means a volcano is at baseline. Level 1 means low-level unrest, abnormal but not yet threatening. Level 2 means moderate unrest. Magma is likely at depth, and entry into the permanent danger zone is already prohibited. Level 3 means magma is near or at the surface, and a hazardous eruption within weeks is possible. Level 4 means a hazardous eruption is underway or imminent within days. Level 5 means the eruption is occurring and causing damage beyond the volcano's immediate flanks. Mayon has been operating near the top of that scale during its paroxysmal phase. That means the 6-kilometer permanent danger zone, a radius around the summit, is fully evacuated. Farther out, an extended danger zone of roughly 10 kilometers applies in the direction of active lava flows and pyroclastic density currents. The communities displaced from those zones are not sitting at home watching this unfold. They are in evacuation centers, waiting. Those evacuation centers are not abstractions. Albay Province, which sits at Mayon's foot, has one of the most practiced evacuation cultures in Southeast Asia, precisely because this volcano erupts often enough that entire generations have done this before. Families know the routes. Local government units pre-position goods. But practice does not mean easy. Farming families leave crops in the ground. Fishing communities leave boats on the shore. And every day away from a livelihood is a cost that doesn't appear in any hazard bulletin. Then a magnitude 6 earthquake hits Eastern Samar, roughly 300 kilometers to the north. While all of this is already in motion, damage is expected. That was the language in the bulletin, and it is blunt language for a government agency. Structural damage, possible landslides on slopes loosened by recent rains, and aftershock sequences that keep already anxious populations from returning to buildings they're not sure are safe. The earthquake doesn't pause the volcanic emergency. It layers on top of it. The compounding is the story. Any one of these events in isolation is manageable. The Philippines has managed each of them before, separately. What makes this window different is the simultaneity. 4 elevated volcanic alerts, a damaging earthquake, and the monitoring agencies working with a depth disagreement that hasn't been resolved. The people in those danger zones are not waiting for the science to settle. They're already living the answer. And that simultaneity, 4 volcanic alerts, a damaging earthquake, the monitoring agencies in disagreement, isn't a Filipino anomaly.
It's the Philippines doing what the Philippines has always done, inside a system that does this constantly. The Ring of Fire is not a metaphor. It's a 40,000-kilometer chain of subduction zones, collision boundaries, and volcanic arcs that encircles the Pacific Basin, accounting for roughly 90% of the world's earthquakes and about 75% of its active volcanoes. The Philippine Arc is one segment of that chain, sitting at the edge of the Philippine Sea Plate as it grinds westward and dives beneath the Asian continent. The plate is moving at roughly 70 millimeters per year, fast in geological terms, which means stress accumulates quickly and releases often. Historically, the pattern repeats. In 1991, Mount Pinatubo erupted in one of the largest volcanic events of the 20th century, and in the weeks surrounding that eruption, the Luzon region registered dozens of significant earthquakes, including a magnitude 7.7 just 2 months before the main blast. Researchers have debated ever since whether the seismic activity destabilized the magma chamber, whether the chamber's inflation altered stress on nearby faults, or whether both were responding independently to the same deep tectonic driver. The answer, still contested, is probably some of each. Japan runs the same pattern on a different segment of the arc. The 2011 Tohoku earthquake, magnitude 9.0, was followed within months by elevated unrest at multiple Japanese volcanoes, including Shinmo-dake, which had its largest eruption in 52 years just 2 months after the quake. Researchers documented stress transfers propagating through the crust at measurable rates. The arc responded as a system, not as a collection of isolated features. Indonesia, directly south of the Philippine Arc on the same subduction network, averages more volcanic eruptions per year than any other nation on Earth. In 2018, Anak Krakatau's flank collapse triggered a tsunami that killed more than 400 people. And that same year, the Lombok and Sulawesi earthquake sequences caused thousands of casualties. The events were geographically separate. They were tectonically adjacent. What history tells us then is this: when multiple volcanoes elevate simultaneously in a subduction arc, and a significant earthquake occurs in the same window, the instinct to look for a connection isn't paranoia. It's pattern recognition. The arc is a coupled system. Energy moves through it. The question is never whether these things are related in some broad sense. They share a root cause, which is the plate convergence driving everything. The question is whether they're linked in the specific, mechanistic short timescale way that would change what comes next. Right now, scientists watching the Philippine Arc are running exactly that calculation. And the answer has consequences for every community inside those danger radii. So here is where we are: a paroxysmal eruption at Mayon, a magnitude 6 earthquake less than 48 hours later, Canlaon and Marapi still active, 4 volcanoes on simultaneous alert, and a depth disagreement between the two agencies monitoring the quake that hasn't been resolved, which means the fundamental mechanics of what ruptured are still in question. The 72 hours after events like these are when the trajectory gets set. Not because scientists are waiting to see if something dramatic happens, though it might, but because the data that comes in during this window is the data that determines whether the system is stabilizing or loading.
At Mayon, the critical signal is whether SO2 flux is declining. Sulfur dioxide output is the clearest real-time indicator of how much fresh magma is degassing near the surface. A paroxysmal eruption can mark a pressure release, or it can mark the opening of a pathway that makes the next eruption easier. The gas numbers tell you which one you're watching. For the earthquake, the aftershock sequence is the read. A crustal rupture at 10 kilometers produces a different aftershock geometry than a subduction event at 73. Which pattern emerges in the next 72 hours will go a long way toward settling the depth argument, and toward telling seismologists whether the stress field in Eastern Samar has been relieved or redistributed. And across the arc, the question the monitoring teams are holding is whether any of the other elevated volcanoes show a step change in their own signals following the quake. A pressure pulse moving through the crust doesn't announce itself. It shows up in tiltmeters, in tremor frequency, in the quiet inflation of a flank that wasn't moving yesterday. What we know right now is that the Philippine Arc is in one of its more active windows in recent memory. What we don't know is whether the events of the last 48 hours are the peak of that window or the beginning of it. The next 72 hours won't give a final answer, but they'll tell us which question to keep asking.